The reaction mechanism we're going to look at now is nucleophilic substitution. Now, this as a reaction mechanism is probably the most basic you will learn across the whole 2 years of your A-level chemistry. And because of that, you need to be beyond confident with this. You need to be so comfortable with nucleophilic substitution because it introduces all of the basics really well. It will introduce what a nucleophile is, it will introduce what substitution is, it will introduce what a curly arrow is. It introduces how conditions can change reactions. So you need to be so confident with nucleophilic substitution that you can do this with your eyes shut. I'd advise against it, but you know what I mean. So this is the reaction we're going to look at. Bromoethane, we're going to react it with sodium hydroxide, and it's going to produce ethanol and sodium bromide. Now, with all organic reactions, when we're looking at the mechanism, we have to consider the conditions. So what are the conditions for this reaction? Well, we've got an aqueous solution. So that means that the bromoethane and the sodium hydroxide are both dissolved in water at the start of this reaction. And we're going to do it under reflux conditions. Now, when we do alcohols, you'll learn a lot more about reflux and distillation. But for now, just learn the conditions are reflux. Basically, that just means that you're going to heat it up in a reaction vessel, probably a round bottom flask. And as you heat it up, some of the chemicals, some of the ethanol and the sodium bromide, well, mainly the ethanol, and potentially the bromoethane, will evaporate. As it evaporates, it will go up into a condenser. And when we're doing reflux, the condenser is vertically above the reacting vessel. So it will go up into the condenser, it will condense, and it will fall back down into the chamber where the reaction is happening. So nothing is escaping from where the reaction is happening. Nothing can be distilled off. Everything's going back into the reaction. And that means the reaction is just going to keep on going until the very end, until everything's reacted. And we've just got ethanol and sodium bromide, or as close as to that as we can. So that's why we're doing reflux. And we're heating it up just to get it going. Now, one of the things about being an aqueous solution, you know that sodium hydroxide is soluble. So that's actually going to be sodium ions and hydroxide ions. And the sodium bromide is soluble. So that's going to be sodium ions and bromide ions. So that actually means that this sodium is a spectator ion. And therefore, we're not actually going to include it when we're talking about the mechanism at all. Because it's sodium ion in the products, in the reactants, it's a sodium ion in the products. So we can basically ignore it. That sodium could be anything. Could be calcium, could be potassium. We don't care. As long as we've got a hydroxide, it will form a bromide at the end. So let's look at what's actually going on in this reaction. And this is the mechanism. So draw out your bromoethane. I'm going to do it as the displayed formula, but there's actually no need. You can do it however you want. And certainly in the more recent exam papers, they've started doing these with skeletal diagrams, just to add an added bit of complexity. So that's the bromoethane, and we're going to react it with sodium hydroxide. But like I said, the sodium is just a spectator ion. We don't care about it. So we're just going to draw the hydroxide. Now, I'm going to draw the hydroxide like that. We put the charge on it, and the charge we put on the oxygen, because that's actually where the extra electron is. And we've drawn the lone pair on the oxygen. That's absolutely vital that you draw the lone pair, because we're going to start drawing curly arrows, and curly arrows show the movement of a pair of electrons. So it has to start at a pair of electrons. A lone pair is a perfectly good pair of electrons. Now, next thing we need to draw onto the bromoethane are any partial charges. Now we know carbon bond, that's not polar. Carbon hydrogen bonds, we don't class that as polar. The carbon bromine bond definitely is polar. So the bromine is going to be delta minus. The carbon is going to be delta plus. So we've got delta plus carbon, a delta minus bromine. So now for the actual mechanism. What's going to happen? Well, we've got a hydroxide ion. That's got a lone pair it's got a negative charge. It's going to be attracted to something positive. So the hydroxide is going to act as a nucleophile. And the lone pair on the hydroxide is going to be attracted to something positive. And the only area that's positive on our bromoethane is the carbon next to the bromine. So draw your curly arrow and draw it carefully. So it starts at the lone pair on the hydroxide and it goes to the carbon with a delta positive charge. So we can say that the nucleophile has attacked that carbon because it's been attracted to it. And there's going to be a bond formed there. Now, AQA don't worry about this, but other exam boards do. And if you move on to chemistry further, this will also matter. I've drawn the curly arrow going, basically attacking the carbon from behind. So attacking it from the opposite direction to the bromine. And that's the correct way to draw it. If you think bromine is quite a big atom, so for the hydroxide to attack from the bromine side, it's got to get past quite a big atom. So that's not going to be an easy thing to do. The bromine physically is in the way because it's a big atom. Also, the bromine has this delta minus charge. The hydroxide has a delta minus charge. There's going to be some repulsion if it tries to come in from the bromine side. So it does actually come in and attack from behind, if you think that's what's going on. Now, the hydroxide, acting as a nucleophile, it has donated its pair of electrons to the carbon. It's formed a covalent bond with that carbon. Now, the carbon has too many bonds. Carbon should only have 4 bonds, 8 electrons around it. But once the hydroxide's attached to it, now it's suddenly got 10. It doesn't want that, so it needs to get rid of a pair. And all of the covalent bonds around it are pairs of electrons, so which of them is going to break? If you think about it logically, which of the pairs of electrons is the carbon kind of least invested in? It's going to be the carbon-bromine bond. So bromine is more electronegative than carbon. That means the electron density is closer to the bromine anyway. So actually the electrons in that carbon-bromine bond are less linked to the carbon than any of the other bonds around the carbon. So that's the bond that's going to break. And to show that that's the bond that's breaking, we draw another curly arrow. Curly arrow has to start from a pair of electrons. So it's going to start from the covalent bond between the carbon and the bromine, and the electrons are going to move onto the bromine. And that's the reaction mechanism. So when we draw what's actually formed, the carbon that has just got hydrogens on doesn't get involved at all anyway, so that stays exactly the same. And now what's happened on the carbon that did have the bromine on, it's now got a hydroxide attached to it, which is what the first arrow, curly arrow, represented. And we've also formed a bromide ion. Now, the pair of electrons from the covalent bond between the carbon and the bromine both went to the bromine. So if we just think for a second about what that bond would actually look like, we just draw a really simple dot cross diagram. Bromine normally has 7 electrons around it, and one of those was in the covalent bond, and there was also an electron from the carbon. So even though we got rid of the carbon and both of those electrons in the covalent bond went back to the bromine, originally one of the electrons already belonged to the bromine. So really the bromine has only gained 1 electron that it didn't have originally, and that's why it only has a 1 minus charge, but both of the electrons went to the bromine. And again, the Br minus is in this reaction, but not in the top one, because in the top one we've written it as sodium bromide, but because it's in solution, we've just got sodium ions and bromide ions. So that's nucleophilic substitution. The nucleophile attacked the carbon because the carbon had a delta plus charge because there was a polar carbon halogen bond, and then the carbon-halogen bond breaks off. So the hydroxide and the bromine swap places or substitute places. That's why it's a substitution reaction. Now, it doesn't have to just be with hydroxide. We can try it with another nucleophile. And that's what this one here is going to be. Now, this time, again, we can draw it out. So we've got bromoethane, and this time, what we're going to react with is potassium cyanide. Cyanide is a really common nucleophile, and it's a really, really useful nucleophile, and I'll talk about why it's a useful nucleophile in a minute. So again, we need to think what the conditions are. So again, we're going to heat it under reflux. That's going to make it go as close to completion as we can. And this time, rather than being an aqueous solution, it's going to be a mix of aqueous and ethanolic solution. That means that it's dissolved in water and ethanol. So rather than dissolving it in water, we're also dissolving it in ethanol, and that just encourages the solution to react as well. But because we're working in a solution, potassium cyanide and potassium bromide, they're both soluble. So the potassium this time is going to be the spectator ion. So we've got a K plus spectator ion. And therefore, it doesn't get involved in the reaction mechanism that we're going to draw. And the nucleophile is just going to be a cyanide ion. Now, a cyanide ion is going to be a carbon triple bonded to a nitrogen. Actually, let's draw it out properly, shall we? It's going to be carbon triple bonded to a nitrogen. It's the carbon that has the extra electron, so the minus is on the carbon, and the lone pair that we care about is on the carbon. The partial charges on the bromoethane are the same as before. Delta plus on the carbon next to the halogen, delta minus on the halogen. And the powerful thing about a reaction mechanism is that, yes, I'm doing this with a different nucleophile. I'm now doing it with a cyanide ion rather than a hydroxide ion. The mechanism is identical. The lone pair on the nucleophile attacks the delta positive carbon. Again, it will go from behind. My curly arrow drawn from the lone pair to the carbon. I've made it and drawn it like that so the examiner can have no issues at all that it's definitely coming from a lone pair, definitely going to the carbon. If there's any possibility that the examiner could argue that that's not where the curly arrow has gone from, you've not drawn the curly arrow good enough. Now my carbon's going to have too many bonds, so it's going to want to lose some electrons and it's going to break the carbon-bromine bond. This time I'm going to draw the curly arrow going underneath. It doesn't matter. It still started from a bond, pair of electrons, going to an atom. That's fine. And if we look at what's formed this time, that carbon doesn't change. This carbon gets a CNH and we attach the cyanide onto here. And again, we form the bromide ion. Now, for those of you that are paying loads of attention, you'll notice something interesting has happened here. I started off with bromoethane because my longest chain is only 2 carbons long. But what I produced is a propane nitrile. So I started off with a carbon chain which was 2 carbons long. I've turned it into a carbon chain that's 3 carbons long. So I've increased the length of the carbon chain. And that is an important thing that this reaction can do. Also makes it trickier when you're naming it. Don't forget that it makes it longer. And if they gave you an exam question of show me the reaction, show me a nucleophilic substitution reaction mechanism to make butane nitrile, you'd have to remember I'm making butane nitrile. I need to start with a, let's say, bromopropane, because it increases the length of the carbon chain by 1. final thing to show you, let's say rather than drawing it out the displayed formula, we do it skeletally. So I've got this bromobutane. What the reaction mechanism would look like here. I'm going to do this one with the hydroxide again. The curly arrow needs to go from, let's put on the partial charge actually, so the bromine is delta minus. The carbon, which is attached to the bromine, that's going to be the thing which is delta plus. So the delta plus is basically that carbon where you can see the bend in the skeletal chain. So your curly arrow, make sure it's obviously starting from the lone pair, and then make sure it's clearly pointing to the carbon. So clearly pointing to the apex of your skeletal chain. That's where the carbon is, and the other one will break from the bond between the carbon and the bromine, and it will go to the bromine. It's absolutely fine to actually draw the curly arrow starting on the line. That's absolutely fine, but that's what it should look like if you asked to draw it skeletally. And again, same mechanism works for hydroxide or cyanide, just remember there's a slight difference in the conditions, and that's nucleophilic substitution.